Okay, and then 9 carbons. Okay, 9 carbon, yeah, should be non something. Okay, and there's the theta bond. Okay, so you need to give location number for this theta bond. Okay, so yeah, non 3 in. Okay, you can put the 3 before n is also fine. Okay, all right, and also yeah, we need to tell people there's the amide in the molecule. Okay, so that's we need to replace final E with amide. Okay, don't need to give a location number because that's the terminal functional group has to be carbon number 1. Okay, and then next we take off the substituent group. Okay, so we have the 2 methyl, one's got the nitrogen, one's on the main carbon chain. We label it N7 dimethyl. Okay, and then ketone. Okay, so ketone as a prefix. Okay, so should be called oxo. Okay, and then we list the alphabetic order before the parent name. Okay, so that's should be 7 dimethyl. Okay, and then so that's the 6 oxo. There's no space between O and N. Okay, so that's one word. Okay. All right, so that's the main part. Okay, but no done yet. Okay, so we have to give stereo alignment for the theta bond and also this chiral center. Okay, theta bond easy figure out. Okay, that should be E. Okay, so trans. Okay, and for this chiral center. Okay, so the hydrogen. Okay, already point away from you. Okay, that's hydrogen. Okay, so that's we call the lines. Okay. So there's this branch. Okay, so higher priority than this branch, and then then followed by the methyl group. Okay, so that's we draw the arc from 1 to 2, and then 2 to 3. Okay, so that's looks like counterclockwise. Okay, so should be S. Okay, so then the full name should be SE. Okay, S for steric center alignment, E for the theta bond alignment. Okay, and then followed by hyphen and 3 dimethyl something. Okay. So don't need to give a location number for the steric center and also a theta bond because there's only one steric center, one theta bond. Okay, so that's people know it. Okay. All right, so now we move to the even harder one. Okay, so that's this Newman projection. Okay, so Newman projection. Okay, so normally speaking, I ask you guys one more thing. Okay, so I want to summarize here. Okay. So last night when I greeted you guys quiz 4. Okay, so a lot of students got confused about the nitrogen containing the functional group. Okay, so a little bit summarized here. Okay, so first is amine. Okay, so amine you have NH2 or NHR or NR2. Okay, so that's amine. Okay, so if there's the aldehyde group. Okay, I mean the carbonyl group. Okay, connect to with the amine. Okay, that's not amine anymore. Okay. Again, okay, so can be H2, okay, HR or R2, okay. So if that if aldehyde, okay, carbonyl group connect to nitrogen, okay, so that's become amide, okay. And then NO2, okay, so now there's one question in the probably the quiz 4, okay, so the dinitro, okay, so a lot of students don't know what's nitro, okay. So nitro is NO2, okay. And the last one kind of the nitride compound, okay, CN, okay, CN2 bond, okay. Right, so no, make sure you know what's their difference, okay, so and then can draw their structure, okay. Okay, so for this compound is the Newman projection, okay. Normally speaking, kind of I ask you guys convert to that structure and you name it, okay. And here I try to directly name it and also try to directly design RS, okay. So okay, so some question. Oh, okay. The chiral center is this one. So chiral center is the carbon with 4 different attachments, okay, 4 different attachments, okay. So we have carbon, methyl, ethyl, and this branch, okay, 4 different attachments. That will be chiral center, okay. All right, we'll go back to this one, okay. So we try to no dash between. No, nothing between, okay. So that's letter, no space, okay. Letter, no space, okay. All right, we'll go back to this one, okay. And so we try to directly name it, okay. So again, same thing, okay. So you try to find the highest priority group, okay. So that's the alcohol, okay. So this compound we name as alcohol, okay. So and then we find the longest carbon chain with OH group attached, okay. So that's go this direction, okay. And we try to give OH group a lower number. That's 1, 2, okay. So then this front carbon, okay. So that will be 3. This bar carbon will be 4, and then the long carbon go this direction, 5, 6, okay. So totally 6 carbon in the long carbon chain, okay, and then that should be called hexene, okay. Put the name here, okay. All right. So now you also need to give the location number for the alcohol, okay. So yeah, you can put the location number here, okay. 1 hexene, no, okay, or put it between N and also, yeah, that's fine, okay. So either way is fine, okay. Okay, and then next, okay, so yeah, there are 2 methyl group, okay, as second group, okay, so on the main carbon chain, okay, so one is on the 3rd carbon, one on 4th carbon. Then we need to put here before the parent name, okay. That's 3, 4 dimethyl. So there's a hyphen between Y and also the 1, okay. So that's not too much space left between, okay. So 1, 3 dimethyl hyphen 1 hexenol, okay. So okay. All right, and then that's not done yet, okay. So more difficult part come to the how do we RS, okay, for 2 Chiral centers, okay. So there are 2 Chiral centers, okay. One is carbon 4, okay, and then one is carbon 3, okay, C4, C3, okay, because these 2 have the 4 different attachments, okay. So all other carbon has either 1 or maybe 2, okay, has kind of some different kind of have same attachment, only these 2, okay. All right, so here I want to show you guys kind of how do you directly assign R and S, okay. So normally I ask you guys can convert to \, okay. Here I show you another way, okay. All right, so for the 4, okay, so the lowest priority definitely the hydrogen here, okay, hydrogen, okay, and then there's the 3 cyclic group, okay. One kind of this methyl, okay, another is this branch, okay, and then the 3rd one, okay, last one kind of this carbon 4, okay. So that's 4 attachment on the carbon 3, okay. All right, now we assign a party, okay. So lowest one definitely the hydrogen, okay. And then what's the highest one? Highest one actually kind of carbon 4, okay, carbon 4, keep in mind. Because carbon 4 has 2 carbon attached to it, here and here, okay, here, okay, 2 carbon, okay. And then this carbon, okay, so the carbon on the left, okay, only has the 1 carbon attached, okay, so that's the lower part, okay, so so this highest one, and then followed by 2, and then 3, and 4 here, okay. Okay, so next kind of the how do you draw the arc? That's kind of hard part, okay. So you have to try to visualize the case with so this is bond come out of you, okay, and then that's the carbon 4 is kind of highest priority, okay. So then also like this, okay, goes to carbon 2, and then carbon 2 goes to carbon 3, okay. So maybe use another color, okay, you can see a little bit clearly. Right. So if you can visualize it, okay, so that should draw kind of the counterclockwise, okay. So that means the carbon 3 should be the S, okay. Right. So now we move to carbon 4, okay. So a little bit too crowded here, okay. So carbon 4, okay. So also has the 4 attachment, okay. So one's hydrogen, okay. So maybe use another color, okay. This one, okay. Another one is acyl group, okay. And then another one kind of this methyl group, okay. And then the last one, okay. So that's the carbon 3, okay. So go front, okay. Go front, okay. So point towards you, okay. So carbon 3, this guy, okay. All right. So then with the priority, okay. Carbon 3 has high priority because carbon 3 has the 2 carbon attached to it, okay. And then followed by this acyl, and then followed by this methyl, and then followed by this hydrogen, okay. Okay, so now you have to kind of the little bit try to develop kind of a vision, okay. So come out of it towards you, okay, and then carbon 3, okay, carbon 3, okay, and then carbon 3 goes to the acyl, and then goes kind of methyl, okay. So pretty much like this, okay. So so if you can develop this kind of vision, okay, so you should directly design kind of RS for the carbon 4, okay, also carbon 3, okay. So if you draw this arc, you find that looks like a clockwise, okay. So that means the carbon 4 should be R, okay. So that's full name, okay. 3s, yeah, 4r, 3, 4, yeah, the dimethyl 1 hexenol, okay. All right, okay, so that's here the yeah, last question, okay. Right, and then we'll continue yeah, the chapter, yeah. We'll continue yeah, the chapter yeah, 7, okay. So here, yeah, I know it's kind of vacant, okay, but yeah, today we cover some most difficult yeah, knowledge in chapter 7, okay. So yeah, please yeah, still need to be the focus on, okay. Please need to be the focus on, okay. Right, and so last time we talked about the diastereomer, okay. Diastereomer are kind of yeah, stereoisomers, okay, but not yeah, mirror imaging, okay. So yeah, right. So example is kind of yeah, diastereomer with multiple stere centers. So here's kind of example yeah, with different kind of stere centers, different chiral centers, okay. And 2 chiral centers, okay, totally you can have with the 4 yeah, yeah, stereoisomers, okay. And then yeah, if you that RS, okay, so yeah, yeah, clearly you can find yeah, yeah, one's R, another SS, and RS, SRK. And then yeah, yeah, RRSS clearly kind of yeah, enantiomer to each other, okay, because they are kind of mirror imaging, kind of reflect for the old atoms, okay. And same thing for the yeah, RS, SR, this pair, okay, so yeah, clearly mirror imaging to each other, okay, and then enantiomers, okay, so that's here the 2 pairs of enantiomers, okay. Right, and then come question kind of yeah, what's relationship between kind of yeah, 1 and 3, 1 and 4, and then 2 and 3, and 2 and 4, okay. So for those pairs, okay, so yeah, we have 1 stere center same assignment, okay. For example, yeah, yeah, 1, 3, okay. So the top carbon, both are R, okay, but bottom carbon, okay, so one is R, one is S, okay. Something, some kind of opposite, okay. Those, yeah, we call the yeah, diastereomers, okay. So yeah, for this case, okay, so yeah, totally yeah, 4 pairs of yeah, diastereomer, okay. 1, 3, 1, 2, 1, 3, 1, 4, and then 2, 3, 2, 4, okay, so yeah. From here, you can see clearly, okay, so for the diastereomer, okay, so one way to identify a relationship between 2 molecules, whether a diastereomer or not, okay. So look at kind of yeah, yeah, chiral center assignment, okay. Some chiral center have same assignment, some chiral center kind of opposite assignment, okay. Right, and then we already learned some yeah, yeah, diastereomers, okay. So yeah, one is kind of yeah, cis trans for arcane, okay. So yeah. You can see, okay, so some stere center has the same alignment, some stere center kind of opposite alignment, okay. And another is kind of yeah, the cis trans for substitute yeah, cyclohexene, okay, or cyclo kind of arcane, okay. Some same, some opposite, okay. Right. And the more common kind of the diastereomers is kind of the yeah, molecule with multiple stere centers, okay. And then you can see here, okay, there is a pair of the yeah, diastereomers, okay. So yeah, 1 chiral center has yeah, the same assignment, both dash, okay. 1 stere center, okay, opposite assignment, okay, 1 dash, 1 wedge, okay. Okay, so now yeah, we do a little bit of practice, okay, help you understand, okay. So yeah, what's your real yeah, yeah, enantiomer and also the yeah, diastereomers, okay. Okay. So we have yeah, these 4 molecule, 3 molecule, A, B, C, okay, 3, okay, right, and then they are stereoisomer to each other. Stereoisomer is kind of yeah, the same connection, but a different pointing, okay, different kind of orientation of bond, okay, right. So now yeah, you guys yeah, practice on it, okay. So yeah, determine the yeah, their relationship, okay. What's here the A and the B, okay. So are they enantiomer or diastereomer, okay. And then A and C, okay, are they enantiomer or diastereomer, okay. And then okay, B and C, okay. All right. Yeah, take a try, okay. Yeah, if someone like, you can put your answer in the chat window, okay. Yeah, definition for enantiomers, okay. So yeah, 2 molecule, okay, mirror imaging but non-superimposable, okay. And then definition for diastereomer, okay. So yeah, 2 stereoisomer as long as they are not here enantiomer, that will be the diastereomer, okay. And the more directly way to do it, okay. So yeah, if you like, you can write it down, okay. Actually, this one we talked about last time, okay. So enantiomers, okay. So yeah, all the chiral center, okay, are opposite, okay. Okay, so not opposite, okay. So yeah, so one chiral center in one molecule are another chiral center in one molecule, yeah, has become S, okay, opposite, okay. So diastereomer, okay, so we just talk about it, okay. Okay, some kind of stereocenter of same enzyme, okay. Some chiral center, same, okay, and then some chiral center opposite. Yeah, okay. So that's the relatively easy way to design our stereoisomer. Okay, so yeah, diastereomer or enantiomer. Okay, okay, someone put. Yeah, that's pretty good. Okay, very good. Okay, so someone already provided the answer. Okay. So A and B are diastereomers. Okay, so yeah, because yeah, okay, so I just put a DR. Okay, maybe full name. Okay. Okay. All right. Some are same case. You cannot hear. These are same. The middle also same case. And then but yeah, these two kind of opposite. Something some opposite case. So that's their same case. And same thing for the A and C case. So yeah, some same case. So this the same, but another two kind of opposite case. So these two opposite. Okay. So these two. Okay. All right. So that's also their case. Okay, and then in the case B and C case, B and C are all are opposite case, all opposite case. So, all opposite case. So that's the yeah enantiomer case. Question. Yeah. So opposite means here the yeah one stair center is R, another stair center will be S. Okay, so that's opposite case. One yeah is S, another be R. Okay. So one directly way to view right, okay, so that's here the just here the dash of wedge, okay. So if one stair center connected by dash, another stair connected by the wedge, okay, has to be kind of opposite, okay. So that's but if you like, you can practice kind of design RS for these three molecules, okay. So yeah, opposite, okay. So yeah, same means here the if the R still R, S is still S, okay. Okay, so yeah, that's make sure that especially this sentence you need to record it. Okay, so that's help you identify kind of the relationship between two molecules. Okay, right. So far diastereomers we talk about kind of two chiral centers. Okay, a different attachment. Okay, so chlorine, bromine, hydrogen, OH, methyl hydrogen. Okay, but yeah, when we come to kind of the molecule with multiple stair centers, okay, but they have same attachment, okay, we call identical kind of chiral centers, okay. Situation get more complicated, okay. So yeah, for example, okay, so yeah, this molecule has two chiral centers, okay. So one has kind of hydrogen, methyl, and then chloride attached, okay, and then another one hydrogen, methyl, chloride, okay. So that's we call identical chiral centers, okay. Right. So yeah, it is supposed kind of the two chiral centers should have the full stereoisomer, okay, SSR, RS, SR, okay. And then if we look at kind of SSRR, okay, so yeah, those two looks like here the mirror imaging to each other, okay. And then if you try to kind of superimposable each other, but yeah, no, okay, so that means kind of non-superimposable image, okay. So yeah, SSR should be a pair of the enantiomers, okay, that's for sure, okay. But the tricky thing comes to kind of RS and SR, okay, right? So yeah, for the SR, okay, so this one, okay, so yeah, if you rotate the molecule, okay, in this way, okay, like this way, okay, 180 degrees, okay, 180 degrees, okay, this here the chlorine will goes here, okay, goes here, okay, and this chlorine will goes here, and this muscle going down, and this muscle going up, okay, and exactly you find kind of here the come to same structure as here, okay, RS, okay, same thing, okay. So that means yeah, super impossible, okay? So these two actually kind of identical, okay? Identical, same molecule, okay? All right, and then yeah, if you take second look of this molecule, okay, you find there's the mirror imaging, okay, can castle this molecule, okay, can castle this molecule, okay, and make half its mirror imaging to another half, okay. So you see kind of here, okay. So last class we already learned that if one molecule has the symmetry plane, okay, castle one half is mirror image to another half, this molecule should be a chiral, okay. Right. So now we come to a very interesting compound, okay. So this compound has chiral centers, okay, okay, but overall, okay, this molecule is achiral, okay, achiral, okay. So this type of compound we call the Miso compound, Miso compound, achiral, okay, that's the symmetry plane, okay. And so yeah, for this compound, okay, with the two identical the chiral centers, okay, actually only three the stereoisomers, okay. One pair of the enantiomers, okay, and then two pairs of the diastereomer, okay. So SS is the diastereomer to RS, and also the RR is also diastereomer to the RS, okay. You can see kind of one stereo center, same alignment, another opposite, okay. Same alignment here, another opposite, okay. Right, and here comes kind of the another difficult conception for the this chapter, okay. So what's the Miso compound, okay? So actually kind of pretty easy, okay? So just write it down, okay? So just two conditions as long as fulfilled, it will be Miso compound. First, there are kind of two or more, okay? Let's say label two more, okay? Chiral centers, okay? Or stereo center, okay? And then second, okay, the whole molecule is kind of achiral, okay? Yeah. So now you can see kind of for one molecule, if it's there are chiral center in the molecule, okay. So this molecule could be kind of achiral, okay. So that's be called a Miso compound, okay. Right, okay. So yeah, theoretically speaking, kind of we should get the two chiral centers should get four stereoisomers, okay. But because of the Miso compound, okay, so there's kind of less than maybe less than kind of 4, okay, so because some kind of identical, okay. And but it will those only happen for the kind of molecule with 2 or more chiral centers, okay. So yeah, if one molecule with only one chiral center, okay, it will be very safe, okay. This molecule has been kind of chiral, okay, so it will be chiral, okay. And also for n chiral center, okay, theoretically speaking, okay, so should be 2 to n stereoisomers, okay, but that's only maximum number, okay. And so reality, okay, so could be less than 2 to n, okay, because they are Miso compound, okay. Right, and the Miso compound, okay, so for you guys, easy, kind of identify, okay. So they contain identical chiral centers, okay, same set of something, okay. So that's shown here, okay. Identical chiral center, okay, same set, okay, methyl chlorine hydrogen, okay. All right, so now we do a little bit of practice, okay. So that's this one actually from last year, the exam, okay. So I will draw 4 molecule, okay, and then you guys tell me which is the Miso compound, okay. All right, so we have 4 molecule here, okay. Yeah, chiral center same as the chiral center, okay, same thing, okay. and actually kind of chiral center included chiral center. Okay, so yeah, Cyclic center included the chiral center. Okay, so for the cis trans arcane, the two carbons we can also call kind of Cyclic center, but normally we don't call it chiral center. Okay, so yeah. Okay, so we do same thing. Right, A, B, C, D, 4 molecule. Okay. Right, ask kind of which miso. Okay. Right, if you like, you can type in the answer in the chat window. Okay, so this morning the self student kind of try to answer this question. Okay, so now don't give the right answer. Okay. Take a try. Okay. We have A, B, C, D. Okay, so yeah, which is or which are. Okay, so yeah, maybe there's more than one miso compound. Okay. All right. Okay. Case in here. Okay, so yeah, definition of a miso compound. Okay, so two or more chiral center, but whole molecule is achiral. Okay. And ABD. Okay. All right. Okay. So yeah, this is a really hard one. Okay. So now yeah, probably I go through this question. Okay. So yeah, so far still no student can provide me all the right answer. Okay. Not all of them. Not all of them. All right. So we do it one by one. Okay. Keep in mind. Okay. Miso compound has have chiral centers, but yeah, no more than one. Okay. So 1 or 2. Okay. Right. So first, okay. So we come to A. Okay. A has no chiral center. Okay. A has no chiral center. Okay. So these two. Okay. So yeah, has two same attachment. Okay. So that's two hydrogen, two hydrogen. Okay. So no chiral center. Okay. So not follow kind of first condition. Okay. All right. So that's A is wrong. Okay. So yeah. Although the A is kind of A chiral. Okay. But here there's no chiral centers. Okay. All right. And then come to B. Okay. B, okay, so definitely kind of two chiral centers, okay, and then there's symmetry plane. Okay, so that means kind of this is A chiral but multiple chiral centers. Okay, B is the miso compound. Okay, all right, for C, okay, so yeah, for C there are also the two chiral centers. Okay, but there's no symmetry plane for this molecule. Okay, so yeah, whole molecule is chiral. Okay, so it's chiral. Okay, so cannot be miso compound. Okay. Right, and then come to D. Okay, yeah, some students can already provide the right answer. Okay, D is a really tricky one. Okay, so last year kind of I remember only one student figured out D is also the miso compound. Okay, D is also miso compound. Okay, so yeah, definitely there are kind of two chiral centers. Okay, but if you take a first look, okay, looks like D has no symmetry plane. Okay, so yeah, but reality. Okay, so yeah, if you rotate the second carbon like 180 degrees. Okay, so yeah, we do this way. Okay. Rotate 180 degrees. Okay, I redraw it here. Okay. Right. So they will keep the first carbon same. Rotate 180 degrees. Okay. So yeah, this SH will going down. Okay. So still straight line. But this methyl group. Okay. So yeah, wedge bond will going up and become kind of dash bond. Okay. Right. Something like this. Okay. And then clearly see kind of there's symmetry plane castle this molecule. Make half kind of mirror image into another half. Okay, so then this molecule is kind of A chiral. Okay, so that means B and D. Okay? Yeah, pretty good. Someone already provided the right answer. Okay, so that you understand what's the miso compound. There are two or more chiral centers, but whole molecule is A chiral. Okay, yeah, very good. All right, and so yeah, there's another type of question. Okay, so I quite often ask in the exam quiz. Okay, for chapter 7. Okay, so yeah, ask identify relationship between two molecules. Okay, are they constituisomer, enantiomer, or diastereomer, or identical? Okay, so those actually kind of as long as you follow rule. Okay, understand what's the definition should be not hard. Okay, so constituisomer. Okay, so just refers to kind of two molecules same formula, but the different connections, two connectivity. Okay, so the starting group on the different positions. Okay. And then yeah, if they have same connectivity, same positions, okay. So yeah, you have to look at kind of the stair centers or chiral centers, okay. So if all the chiral center opposite alignment, okay, that's actually already showed here, okay. Then that will be enantiomers, okay. So if some are same, okay, so yeah, some kind of opposite, okay, so that's we call the diastereomers, okay. So if all are same, okay, so S is S, R is IR, okay, so then that's we call them identical, okay. So yeah, this type question cannot not too easy, okay, and then we can little bit practice here, okay. So yeah, we use the question here. Okay, so enantiomer, constitutive isomer, diastereomer, identical, describe relationship between two molecules, okay. Relationship between two molecules, okay. So has to come to two molecule, okay. And then Miso compound or chiral, okay, describe the property of one molecule, okay. So if I say kind of this molecule is kind of Miso, okay, that's right, okay. But I cannot say kind of this molecule is kind of enantiomer, okay, because have to come in pair, okay. So yeah. And but it will be safe, okay. So the Miso compound has no enantiomers, okay, because Miso compound is achiral, okay. Achiral molecule has no enantiomers, okay. Enantiomer cannot, it's can not here the overlap with its mirror imaging, okay. So that's what we call the enantiomers, okay. But the Miso compound cannot feel it's achiral will overlap with the superimposable with its mirror imaging, okay. So yeah. All right, okay. So yeah, we use this one as example, okay. So this one actually kind of from quiz 4 questions, okay. So last question asked kind of which pair are diastereomers, okay. Actually kind of which pair are stereoisomers, okay. Here I just change the question, okay. Ask you guys kind of what's the relationship between each pair of a molecule, okay. Right. So anyone can have some idea, okay. So what's the relationship between the A, okay, these two molecules? Are they constitutive isomer, enantiomer, diastereomer, or identical? Anyone know? This part should be pretty easy, okay. Anyone know the answer? That's right, constitutive isomer, okay, pretty good, okay. Because the connection totally changed, okay. So one kind of 1,2 dimethyl, another kind of 1,3, okay. So the connection is different, okay. So that should be constitutive isomer, okay. So different connectivity, okay. Now we move to a little bit tricky one, B, okay. What's the relationship between B, okay? This pair, okay. So this pair have same the connections, okay. So yeah, then are they enantiomers, diastereomer, or identical? Anyone figure it out? Yeah, that's right, okay. Should be identical. These two actually kind of same molecule, okay. So if you rotate kind of one molecule like 180 degrees, okay, for example, right molecule, okay, 180, okay, so the two methyl group will point down, okay, and then overlap with this molecule, okay, and then these two will be kind of same molecule, okay. Okay, how about C, okay, what's the relationship between these two molecules, okay? That's also hard one. All right, pretty good. Someone already provided the right answer, okay. Should be diastereomer, okay, diastereomer, okay. So yeah, like said in the class, okay, so whenever you see the chair conformation, okay, so yeah, hard to say, okay, so yeah, immediately change it to the wedge dash structure, okay. The first one, okay, so yeah, both methyl group point up, okay, both methyl group point up, okay, should like this, okay. You convert kind of a wedge bond, okay. And then yeah, you can find kind of if we compare it to another molecule, okay, so another molecule, okay, so yeah, right. One is wedge, one dash, okay, so some same, some opposite, okay, so that's typical the diastereomer, okay. Right, so now what's the relationship between the last pair, okay? These two, anyone can write down the answer. Yeah, that's right. Okay, constitution isomer. Okay, pretty good. Okay, now you guys know it. Okay, pretty good. Okay, because this one kind of 1, 2, another one kind of 1, 3. Okay, different connections. Okay, so totally kind of different connectivity. Okay, pretty good. Okay, so in future we'll practice more this kind of questions. Okay, so that's please make sure you understand what's going on. Okay. All right, so now we move to another hard topic. Okay, so facial projection. Okay, facial projection. Okay, so we already learned the 2 ways to show the stereochemistry of the molecule. Okay, so first one is the wedge dash structure, wedge bond dash bond. Okay, point towards you, point away from you. And another one is the Newman projection. Okay, so the single spot. Okay, and then the big circle. Okay, front carbon, back carbon. Okay, and then third way to show it here is the facial projection. Okay, so to draw the facial projection. Okay, so is to convert here the wedge dash structure to facial projection. Okay, so your first thing you need to do is reorientate, kind of rearrange the molecule. Okay, so you need to make sure that the wedge bond. Okay, so in the horizontal way. Okay, horizontal way. Okay, and then the dash bond kind of in the vertical way. Okay, so like a vertical way. Okay, and then you just go ahead convert all the kind of the bond into a straight line. Okay, so that's the facial projection. Okay, so that's facial projection. Okay. So pretty easy. Okay, but just keep in mind. Okay, because that's assuming. Okay, so all the horizontal line represent kind of the wedge bond. Okay, and also all the vertical line. Okay, so vertical one and the blue one. Okay, so indicated the dash bond. Okay, so in this case when you try to rotate the molecule. Okay, there are some kind of rule you need to follow. Okay, first. Okay, so if you rotate the molecule for 180 degrees, okay, that's allowed. Okay, so no problem. Okay, so for example this molecule. Okay, so I rotate 180 degrees. Okay, so that's we'll rotate the aldehyde going down. Okay, and then this is the alcohol going up. Okay, and then hydrogen going left. Okay, going right. Okay, OH group going left. Okay, so that will be same molecule as here. Okay, no change of stereochemistry. Okay. But if you rotate it for 90 degrees, okay, or 220 degrees, okay, so that's forbidden. Okay, so because if you rotate kind of for example we rotate 90 degrees. Okay, so this aldehyde goes here and the OH goes here, and then this the CH2OH goes here. Okay, hydrogen goes here. Okay, and then that the people get confused. Okay, so originally the wedge bond become dash bond become wedge bond. Okay, totally changes stereochemistry. Okay, so don't do the rotation for 90 and 220 degree rotation. Okay. And also flip are not allowed. Okay, so if you flip the molecule. Okay, so like this. Okay, so that's also not allowed. Okay, because once you flip, okay, so wedge become dash become wedge. Okay, so that's also change the stereochemistry. Okay, so you got confused. Okay, so so only 180 degree rotation allowed. Okay. So actually, facial projection pretty useful to show the kind of molecule with multiple steric centers. Okay, because multiple steric center, you have to draw kind of all the dash line on the wedge line. Okay, so that's not the time consuming. Okay, and then you can directly convert to kind of facial projection. Okay? But still keep in mind. Okay, all the vertical bond. Okay, horizontal bond. Okay, horizontal bond has become a wedge bond. Okay, and then vertical bond has become dash bond. Okay, and then you can directly convert to here. So this same thing to here. Okay. And for the facial projection, and people usually it's a lot. Okay, in the biology. Okay, and the reason for that kind of easy to identify the relationship between two molecules. Okay. So here kind of the two example. Okay, so for the first pair. Okay, so if we show the facial projection, easy to see kind of two steric center all opposite. Okay, so mirror imaging to each other. Okay, and non-super impossible. Okay, so those two should be enantiomers. Okay, and then second pair. Okay, so some steric center are same. Okay, so the top steric center. Okay, same direction, same pointing. Okay. Some kind of opposite. Okay, so the bottom one. Okay, so some same, some opposite. Okay, so typical kind of diastereomers. Okay, and also the facial projection help you easy to identify the Miso compound. Okay, so I'm here. Okay, so they see the Miso compound. Okay, so clearly there are the mirror imaging. Okay, not mirror imaging. Okay, symmetrical plane. Okay, cast this molecule. Okay, half is mirror imaging to another half. Okay. And so yeah, you guys kind of after the learn feature projection, you also need to learn how to kind of design RS, okay, and also yeah, how to name it, okay. So yeah, give you one example, okay. Yeah, for example, yeah, we have this yeah feature projection, okay, and then in exam quiz, I will ask kind of yeah name this compound, okay. So how do you do it, okay? So yeah, actually kind of yeah not hard, okay. So yeah. Very beginning don't need care about kind of the yeah stir centers, okay, stir isomers, okay, or the RS, okay. So go ahead design, okay, and then yeah first find the highest priority group, okay, highest priority group, okay. So yeah, should be kind of this arcing chain, okay, because the chlorine is kind of only for the prefix name, okay. So that's the yeah this, okay. So maybe label you guys, okay. Yeah, that's the yeah main carbon chain, okay. And next kind of yeah, we label this main carbon chain, okay, number it, okay. So yeah, we try to give we have the subsequent with lower number. So that's why we start from this carbon 1, 2, 3, 4. Okay, so 4 carbons, okay, should be built in. Right, and then yeah, chlorine we put before the yeah yeah partner name, okay. So that's yeah 2 chloro, okay. Yeah, 2 chloro built in, okay. Okay, so this is not done yet, okay, because yeah, there's yeah one stir center in, okay, there's Chiral Center also called kind of Chiral Center, okay, 4 different attachment, okay. So now yeah we need design RS, okay. So yeah, then you have to keep in mind, okay, for the all the yeah horizontal bond, okay. So yeah, that's actually kind of the yeah, point towards, okay, and then vertical bond point away from you, okay. That means yeah, it's good for you guys, okay. So this hydrogen point away from you, okay. So that's lowest priority, okay. So point away from you already, okay. And then yeah, we line the party for other 3 K. So that's yeah, one is kind of chlorine, this SO 2, and this methyl 3 K, and then you draw the arc from 1 to 2, 2 to 3 K. So it looks like here the S, okay, counterclockwise K. So that's yeah S. Yeah. So that's yeah. How do you yeah name this compound, okay? And then yeah, give you guys one homework, okay? So yeah. Yeah. So this one you don't need to do it now, okay? So yeah, just the yeah, copy it, okay? So yeah, when you go home, okay, try to practice name this compound, okay? So yeah, we'll yeah go through this question in the yeah class yeah the next day, okay, on Monday, okay? So yeah, so this compound has yeah 2 stir centers, okay? Okay, so you need to give kind of assignment for both. Okay, and for the yeah. Facial projection case, so yeah, there's another types question kind of ask kind of yeah, what's the relationship between 2 molecules? Okay, so that's just say we practiced, okay. So give you one example, okay. All right, so we have yeah the 2 facial projection, okay. So yeah. All right. Ask kind of yeah, what's the relationship between these 2? Okay, so consume isomer, enantiomer, diastereomer, all identical, okay. All right, so for this question, okay, so yeah, if you take first look, okay, so yeah, we find yeah 2 star centers, okay, here, and then this one, okay. So the first yeah, star center pretty easy to identify, okay, because clearly they are mirror imaging to each other, okay. So that means here the first 2 kind of opposite, okay. So I put O here, opposite, okay. Yeah, maybe put O. Okay. Right, and then come kind of the next pair, okay. So this pair kind of hard to say, okay, because yeah. So that looks like the yeah totally kind of yeah mass up kind of orientation, okay, because the one kind of bromine goes to left, okay, this one going down, okay, and C3 go left and goes to right, okay. So yeah, and then methyl goes, I mean goes here down and go here, okay. So here's the other one small tips for you guys. Okay, for this kind of situation, okay, you are allowed to rotate one carbons. Okay, so yeah, one carbons. Okay, but yeah, you can also assign RS. Okay, no problem. Okay, so if whatever comes same kind of or kind of if the same will be diastereomer, if kind of opposite will be the yeah enantiomers. Okay, right. So what you can do kind of yeah, rotate this yeah the bottom carbon 120 degrees. Okay, so yeah, you switch the position. Okay, so yeah. BR going down, and then N3 go NH2 go here, and then CH3 goes here. Okay, and then you can redraw it. Okay, so yeah, if you redraw it, okay, so yeah, the top carbon we keep here yeah just here the same. Okay, and just redraw the bottom one. Okay, right, BR will going down. Okay, and then H2 will go left. Okay, and then CH3 will going to right. Okay, yeah, that's still the same Chiral Center. Okay, so if you rotated one carbon, won't change the stereochemistry. Okay, so that's yeah, won't kind of yeah that like yeah, yeah rotate 120 degree 90 or 270. Okay, so right, and then you take second look. Okay, you find kind of yeah yeah these two. Okay, exactly same thing. Okay, right. So amine to the right, C3 to left. Okay, and bromide kind of to the bottom. Okay, so that means kind of yeah bottom stair center. Okay, they are same. Okay. Same case. So some opposite, some same case. So that means yeah, yeah, these two molecule act kind of yeah, their stereomer. Okay. Yeah. So that's yeah, another application for yeah, yeah. Okay, for yeah, Fisher projection. Okay. And then next topic is kind of yeah, cyclic structure. Okay. So yeah, yeah, really depends on what kind of the substance group. Okay. So and then what's relative positions. Okay. Here's one example. Okay, so we have two different substance. Okay, so yeah, on cyclohexene. Okay, one OH, one methyl, and so yeah, two substance. Okay, so yeah, yeah, you can have two steric centers. Okay, so overall there are kind of four possible steric isomers. Okay, four possible steric isomers. Okay, and so relationship between them kind of yeah, two cis are enantiomer to each other. Okay, mirror imaging. Okay, and two trans also enantiomer to each other. Okay. And yeah, but yeah, if you only name cis and trans, okay, cannot thorough all the kind of yeah full situation. Okay, so that's why yeah for yeah cyclohexene or cyclohexene kind of when we name it, okay, now use cis trans. Okay, so yeah, we always use RS. Okay, because yeah there are kind of two cis and two trans. Okay, so yeah yeah two cis, one kind of RS, another SR. Okay, and then two trans, one's kind of SS, another kind of RR. Okay. Okay. I guess yeah, that's it for today. Okay, so yeah, we continue study the yeah cyclic molecule okay, on Monday. Okay, so yeah, and then any questions? Yeah, today we cover some kind of yeah, the most difficult yeah knowledge in chapter 7. Okay, so yeah, make sure you review yeah yeah all the yeah lecture and slides. Okay.